Hello learners, so let's talk about what is frame of reference. Suppose you are at some workplace or your school and you have some rivals, and obviously your friends will say that when there is a issue or some fight in between you and them, your friends will always support you, and your family will always say that you are correct. Maybe when you are wrong they will say that no, but let's imagine a situation, in a general situation, that they love you blindly and they will say that yes, you are correct. So just like here is you and your friends and your family will see everything in a point of view of yours, and your rivals will see a point of view where you are his rival. And like this, other people will say that your friend is going to say that you are 100% correct. Your rival will say that you are 100% wrong, and this person who is a third person, he is going to say that you are 50% correct and 50% wrong. So you are correct or not, only a wise person can say so. And the wise, we call this wise person in a frame of reference which is inertial. So let's get into the topic. Here you are in a frame where everything is everyone is seeing you in a point of view of yours, and in this point of view you are seem to be correct, but in this point of view of your rival you are wrong, because he is seeing you from a opposite point of view. So just like this in physics, suppose you are standing here and your friend is also here, and a bus is traveling. For both of you, the bus is traveling with a velocity v. But let us suppose you and your friend, you are going in a bike and your friend is standing here alone. For him, the bus is traveling with velocity v, but for you, when you travel with velocity v, the bus is at rest, right? This is what we call is a relative velocity. Here velocity of the bus is v for your friend and 0 for you. Here is relative velocity, but our topic is not about relative velocity. Our topic is about frame of reference, non-inertial frame, inertial frame. So suppose you are here and someone is going on a bike, right? And let us suppose the bike is accelerating with acceleration a vector. For you, for him, it seems to be like you are going backward. You have experienced it, right? When you are going to your grandmother's house in train, you will feel like the trees are going backward and you are at rest. Just like this, when the person is on bike, he is feeling that he is at rest, but you are accelerating backward. So this is something like relative, like you don't know whether you are correct, whether you are wrong, or you don't know about all these things. But the thing, but who can say that you are correct or you are wrong is a person who is watching all these things from a frame of reference, where he is not under any pressure that if he will say that you are wrong, he will feel bad, or if you will say you are correct, he will get praised. So he is not under any pressure. He is in a space where he don't need to worry about anything else than telling the right judgment. So here when the person is at rest and another person is traveling at acceleration a, he will feel like you are going backward, and we are going to find with how much amount he feels like we are going backward. Here you are at rest. Let us suppose the frame is here the frame is, and a person is here and the other person is here, and you are going to be observed. These are two observers, right? So first observer is a person who is in the frame you are in, and the second person is going with acceleration a, means his frame of reference is also accelerating, and here this person is not accelerating. So as this person is not accelerating, acceleration is equal to 0, so here no force is being applied on this person, and hence he is in a inertial frame. But in this case the person is accelerating. His frame of reference from the frame which he is observing you is also accelerating. So this is non-inertial frame. So basically we can say that the non-inertial frame is a frame where we can't apply Newton's law of motion. So and these frames are accelerating frames, where we can also, we know also that when a particle is moving in a circle with constant velocity, even with the constant not velocity, with constant speed also, we can say that the particle is not accelerating, because the angle, right? No, the direction is changing with every time interval. Like here the direction is changed like this. So we can also say that when the reference frame is rotating means the direction is changing every second. The direction is changing every second, that's why it is a non-inertial frame, because due to change of direction there is a acceleration. So direction of change as well as increase or decrease in velocity can make a frame of reference non-inertial frame of reference. Let us know about how to see these things mathematically. So let us suppose there are two reference frames. Here is one, and let us suppose here is a reference frame S, and another reference frame is coinciding with it, which is S dash, but this S dash is accelerating, and after a time interval t, initially it was coinciding with this coordinate system, it coordinate system, it is reference frame, but after some time t, it is now here. Initially both of them were in the same place, but now here is S dash, right? So let us say this x, y, z, and x dash, y dash, z dash, right? Y dash. So let us suppose the acceleration of this frame of reference is a naught. So after time t, we are going to calculate what is this distance. So we know from equation of motion that S equals to ut plus half at square. So ut, here u, initially they were at rest, so u equals to 0, so this term will be 0, and here a is a naught, so finally this distance or S equal to half a naught t square, right? Let me erase it. This is this frame of reference has gone from this point, so therefore we will make this vector like this, and value of this will be half a naught t square, right? So let us suppose there is a point P here. For this frame of reference, its position vector will be r dash. For this point, the position vector will be r. Then we can see a triangle, like this is a triangle, right? So this triangle is just like this. Here is half a naught t square. Here is r dash. Here is r. We know triangle law of vector addition. From this, we can say that r equals to half a naught t square plus r dash. So r equals to r dash plus half a naught t square, right? Now we know differentiation, so let me raise these. R equals to r dash plus half a naught t square. Okay, let's differentiate it with respect to t. So we will get dr by dt equals to dr dash by dt equals to half a naught 2d, right? So let's differentiate it again with respect to t. Again, d2r by dt equals to, sorry, this is plus, and d2r dash by dt plus a naught, right? T will be 1 and a naught. So now let's bring a naught to our left hand side and just flip the equation. d2r dash by dt square, right, equals to d2r by dt square minus a naught. We know that after double differentiating position vector, we will be able to get the acceleration vector. So replacing all these things with acceleration, we will say that this is a dash. I am using dash to represent the acceleration position vector or velocity or whatever with respect to the s dash vector, and here S dash a non-inertial frame of reference, and here I am using general R or S or to represent if anything, any variable or anything from a point of view of inertial frame of reference. So A dash vector equals to A vector minus A naught vector. So now we are going to let's suppose the mass of the particle was m, right? So let's multiply m with this equation. So we will finally get that m a dash vector equals to m a vector minus a naught m a naught vector. Let us assume this minus m a naught as a force F naught, and we know that m a dash acceleration with respect to acceleration of the particle p with respect to non-inertial frame, acceleration with respect of the particle with respect to inertial frame, and these will give force applied on the particle with, from the point of view of in non-inertial frame, and force applied on the particle from S or inertial frame of reference. And now we are going to substitute this F naught here, plus F naught vector. So here is the equation, and from this we are able to see that when we are in an inertial frame, we will see that the a force F vector is applied on the particle. But when we are in a non-inertial frame, we will see that a force that is not even being acted on the particle is also present. Like there is no acceleration a naught due to any force. It is just a fictitious force. What we call is a pseudo force. So let me write this. F vector is equals to F vector plus F naught vector. So this force, when we are in non-inertial frame, we experience a force that is not even being acted on the particle, which is known as pseudo force, because it is fake. It is not real, like a force being acted on the particle, but it is experienced. It is not applied, but it is experienced. We will learn about it more in the upcoming lectures. So pseudo force, when in the lift we are going to lower floors, we feel like some less weight or less force being applied on us. We feel like we are being we feel some freeness. And when we are traveling to upper floors, we feel like some force is being acted on us. We feel like we are being compressed, right? So why this happens? Let us understand this using this equation. So suppose we are traveling in a lift. We are going upward with a acceleration a. Here obviously our weight will be applied downward. Consider the direction as minus n cap, and here as acceleration is upward, we will say that acceleration vector equals to acceleration into n cap, as this is positive negative, our assumptions. And then here force, as this is a non-inertial frame, we can see that easily the frame is accelerating. We are in a non-inertial frame, so we will feel a pseudo force and obviously the real force. So what will be the net force we will feel in the lift? Let's calculate it. It will be equals to F minus mg n cap plus F naught. What will be the value of F naught? F naught equals to minus m a naught, right? So minus m a equals to a n cap, right? So minus m a n cap. So in total we will get that minus m g plus a n cap. So we can see that instead of feeling a force of minus mg n cap, we are feeling a force of minus mg plus a n cap. So here the acceleration has increased, means the force on us has increased. And as when we travel to upper floors, we feel a little bit of excess force on us due to this increase in acceleration. And obviously increase in acceleration will lead to increase in force, and force will be applied on us as we are in this non-inertial frame. So let us consider the second case, where we feel that there is some decrease in force which is normally acted on us. So here we are traveling downward with acceleration a. Force is being applied mg n cap, obviously minus mg n cap. Acceleration is equals to minus direction negative, so minus a n cap. Fixed force will be minus m, a vector is minus a n cap, so minus minus plus a n cap. So total force will from the reference frame of a non-inertial frame. Just remember that the frame of reference is important. It is inertial or non-inertial. So force will be equals to minus mg n cap plus ma n cap, and in total it will be minus mg minus a n cap, right? So now here is a decrease in acceleration. Decrease in acceleration means decrease in force, and finally decrease in force will make us feel like we will feel light.